Okay. So okay. Now, back to our lecture. In the now we know how to reformulate all kinds of nonlinear problems into this standard linearization form. We have slack or surplus variables to make them equality. We have Taylor expansion to make everything linearized, and then we reformulate this whole thing in this way. Okay, now we will rewrite this whole thing in a different way, another way, and that will make our following derivation easier. So usually in LP, we can rewrite this whole thing into the vector form. So when we do it in the vector form, it's actually looking like this. That simple. So this is how you. Maybe I should cut this to here so you can have a comparison, right? We have a bunch of c, the coefficients in the objective function, and if you have c1, x1, c2, x2 until the last one, basically is a dot product of a vector of c with the vector of x. And also all the small a parameters could be combined together into a huge capital A matrix. So that capital A matrix contains all our small a coefficients. And basically the result could be combined together into this matrix form, capital A, the matrix, dot product with our x vector, and ends up with a vector of b. So that's the way we could make our formulation cleaner. Okay, but later on when we try to do something further, we would like to handle square matrix. So over here we know the number of n is larger than m. That means we have a wider a than taller a. We have a wider one. So the horizontal size of A is larger than the vertical size. So if you rewrite, I mean, try to visualize this in this way, you basically have this is a, you know, C dot product with X basically equals to C transpose X, right? And when you transpose C, you have a horizontal one. And your C basically, this is your C transpose. And your X, of course, is a long one. It's like this. This is your X. So this is like a horizontal vector multiplying a vertical one for your objective function. And for your, let me make this shorter because usually, no, the length should be the same, right? The length is the same, but okay. So about the objective function, I mean the constraint function, how it look like could be like this. Okay, this is also your x, but this is your matrix A, and then they multiply together. Um, in order to be able to multiply these two together is to make sure the size here is the same as the size here, right? So you multiply line by line, right? And since we have uh, n equations, so the size here is m, and over here we have n, and we know m must be smaller than n. Okay, so that's why my A matrix looks like a wide matrix, not like a tall matrix. Okay, and what you get at the end is like a vector like this. Oh, sorry. What you get is actually a matrix, a vector B, like this tall, the same size, because the size of B is also m, m components. Okay, Um, from here, you can already see your matrix A is not a square matrix. So you cannot do inverse. And in our further derivation, we would like to have some uh, possibilities of doing inverse so that we can do something further. So in linear programming, we would like to separate all those coefficients in the following way. And this is just one of the example of how we could separate them. We separate them like this. We make a cut. So we make one half of the cut, which is having m components white. So that we have like m by m over here. Okay? So the length on the right hand side becomes n minus m. Okay. And we call the left portion as basic, and we call the right portion as non-basic. Okay, and when we make the cut, we also need to make cuts of our C and also X. Actually, we need to cut everything. So whatever that is having the length of n needs to be cut. So over here, I basically cut like this. Here I have m of them. Here I have n minus m of them. So over here, those become like a x, and we call xb. So basically, these are so-called the basic variables. And the rest, we call them xn. They become non-basic variables. So you probably have questions right now. How do I make this cut? How do I separate them into two groups? Basically, there are some rules later on. But during the procedure of LP, we try to arrange which are the ones that should be categorized as basic and which are the ones that is categorized in non-basic. And by switching their sides, we actually can find a solution. It's quite magical later on. And I will try to explain why this way of doing this could help you find a solution. Okay? So now you only need to know we try to separate those coefficients into two groups. Also, we separate the variables into two groups. Okay, and since we do that, we should have a bunch of XB here, and xn here. So similarly, we have CB and CN. And to be precise, because they are placed horizontally, so I should put a transpose sign here. Okay, so B represent basic, N represent non-basic. Okay, so now you just need to know we separate them in this way. So you can call the left half here as AB, and here is AN. Okay, okay, so we separate them in this way. What's next? Okay, when we do this, we can actually, from here, we can actually rewrite the entire mathematical formulation in the following way. Our objective function actually becomes CB transpose XB plus Cn transpose Xn, right? It's like this multiply with that, plus this multiply with that, correct? Does that make sense? Okay, so just by separating them into two groups, we can already introduce new equations like that. Okay, we can do the same thing for the constraints. The constraints become AB times XB plus AN times XN equals to B vector. Because whatever on over here will only multiply with whatever on top of here. It never multiply with the bottom part. And whatever is on the right hand side here is always multiplying at the bottom. So it's just like you separate their multiplication and then do the summation later on. Okay? And that actually helps us to do further derivations. Okay? So what's interesting is that the concept of linear programming is like this. What if this part is 0? And remember, XAB is a square matrix. So what if ANXB, ANXN equals to 0? Can you tell me what would be the possible situation that this term becomes 0? Say again. No, that's not the answer. But what would be the possible way? This could be 0. Yeah, you're right. There, at the end, you will have one solution, but there's only one chance this could happen. All the xn are 0. Yes, because an could not be 0. They are the coefficients in our problem. They are there already. You cannot never change the value of small a. So all you can change is your x. So when this happens, the only chance is that xn equals to 0. So what if xn equals to 0? Then this whole chunk is 0. Then, just like what you said, this is a square matrix times a vector with unknowns equals to b. And at that point, at that moment, you have same amount of equations with same amount of unknowns. So you will have one solution. So in that case, you will have a b x b equals to b, And you can directly get xb equals to ab inverse b. You get the solution, right? So can we categorize our basic and non-basic variables in a certain way, and then whatever that's inside the non-basic, we say, hey, you guys are zero. Then we get some solution on the basic side. We can solve for the xb using this equation. So how many possibilities are there? We totally have uh, n variables. So the possible combination is a combination of n variables, and we basically choose how many of them? M of them. The combination of n over m. If we have totally n variables, we choose m of them to be basic, so the rest of them become non-basic. So this is the total number of possible ways that could use this trick. The other half, you guys become zero. And on the basic side, I get the solution from here. So I have C and M possible combinations that could be solutions. So linear programming is trying to find solutions from those combinations. But linear programming is trying to do this in a very systematic way so that you don't need to try all of them. You don't need to test all of them. Imagine how many possible cases could be when those numbers are large. Could be thousands of them. If we have a problem that requires thousands of calculations in order to get the optimal, it's a very stupid method. It doesn't lead you to the solution in a smart way. So linear programming will lead you a very smart way to find solutions within those combinations. Okay? So these are the possible combinations. Too many of them. So LP will help you to, you know, find solutions systematically. So how do we do that? Uh, okay, in order to do that, we will play with the equations that we had earlier. So how do we play with it? Okay, this guy. We need this guy here. Copy and then paste. So it seems like when we have the right combination, our XBs are the solutions. There should be a one possible combination that is the solution, and our xn's become zero, and our xb will be the solutions. So let's focus on xb and see how xb look like. We can rewrite this in the following way. Oops, sorry. We would like to derive what xb actually is. So in general, we could rewrite this whole thing in this way. And if, because xb is a square matrix, we could actually get this by pre-multiplying the inverse of xb. Okay, and over here I should place this inverse, AB, sorry, the inverse of AB to every term. So in fact, xb equals to this long equation, okay? But we don't know what is xn yet. And maybe we can use this to do something with our objective function. So let's look at our objective function. We know our f equals to here. We know our f is like this. Maybe we could plug in and see what happened, how this new formulation does to our objective function. So basically, I just plug in. I keep the whole thing, and my xb become what's going on here. I just plug in, and then I keep everything the same. Okay, and I just want to rearrange the whole thing so that we can do some observation of this. So just expand the whole thing and trust your math. So over here, I could kind of combine certain things so that I have CNT, CN transpose minus CB transpose, AB inverse, AN, and then XN. Okay. So if you try to observe this looks very complicated function, you can try to observe this, you will tell this is actually a bunch of coefficients doing some multiplications. So C are the coefficients in the objective function, A part of the coefficient in your constraint, B is what's going on the right hand side of your constraint. Also here, CCAA. Those are basically the coefficients. And so when you have this is basically a constant. And this is also a constant. But what's changing is here, xn. Xn is changing. Okay, we don't know what xn is. So this is actually a linear function. And we need to go back and look at what my original problem is. We guarantee you all the x are positive or 0. So when we go back to here, we realize, okay, this chunk is larger than or equals to 0. So that's where this is positive, right? And how could f be minimized? This is always the same. Um, Not always the same, but I mean, by different choices of basic and non-basic, this value is changing, right? Because we have choices. But we when we make a decision of basic and non-basic, this cannot be changed anymore. Okay, and the coefficient here cannot be changed anymore. So what's left is the numbers that you can decide right here. Okay, so if I would like to make this function smaller and smaller, the only way that is possible is that maybe this whole thing should be negative. Because this part is either positive or 0. If these coefficients are negative, I'm making progress. I'm trying to make my objective function smaller. Okay? So what if this whole thing become negative? It's good for us. Then we can make progress of minimization. If those are positive, then whatever I chose in xn, the value of f is increasing. So you won't be able to make any good on minimization. That's why we try to find possible combinations that this coefficient is actually negative. So this is how linear programming is doing a very systematical way. You basically evaluate different combinations of those, and maybe you can find one possible combination that guarantee this is negative. So you know later on when you try to find different values of x, you are sure f should be decreasing. Okay, so that's the trick. Okay, now we could actually physically try to solve a problem. So here's the example that I'm going to use today. I'm gonna minimize this. Okay, so if you have a problem like this, and of course my x1 and x2 they are positive. Okay, so if you have a problem like this, it doesn't satisfy my standard format. I need to put either slack variables or surplus variables to convert them into my standard format. So let's do that first. Over here, I could rewrite in this way. And now I introduce a new variable, which is x3. Okay, so x3 is a new variable. And I need to make sure x3 is also positive. Okay, so this is uh, my new variables. My new variable, yeah. And the next one, I have negative x1 plus 2x2. Over here, it's a different equation. I need to convert it into a equality one. So I need to introduce a different variable, a different slack variable, which is different from the one I introduced earlier. So I'm introducing a x2 right here. Okay, and for the third equation, similarly, I need to introduce another different slack variable. So I actually have to, because I have three equations, they're all smaller than or equals to, I need to convert them into equal sign. That's why I have to create uh, one slack variable for each equation. So totally, I actually introduce three additional slack variables. And those slack variables has to be larger than 0. Okay, this is how this whole trick uh, works. Okay, and also for our adjective function, in this case, you basically is doing this. And you still introduce coefficients to your objective function, but you introduce slack variables to your objective function, but the coefficient of them are 0. So you actually have this for your objective function. It's just that the coefficients are 0, so that your objective function doesn't change at all. Okay, that's how the original problem and the new problem are equivalent to each other. So now we could rewrite this whole thing in this way. Okay, so this is how the original problem is now converted into this new problem. Okay, and by default, I mean, to be a good start, usually we treat these slack variables as basic. So we treat these as non-basic. So at the beginning, these are Cn, these are Cb, of course transpose. Okay, so usually a nice start is to treat your slack variables as your basic. Okay, and of course there sometimes there will be issues to start because you don't know which are the ones that should be considered as basic. That's a very tricky part. But in this case, I'm telling you, okay, this will be a nice start. Okay, so since I chose the left two column as non-basic, so those are called the A N, and the uh, th- uh, right three columns, they are called the basic. So they are A, B. Okay, you get it? Now we will move on to a next page. And we will examine this based on our derivation. We want this to be negative. So we paste. We wish this to be negative, right? So let's try to calculate this. In this current selection of basic and non-basic. So let's do it. What is my Cn right now? It's basically -1 and -2. What is my Cb right now? It's basically 0, 0, 0. What is my AB inverse? AB inverse, because AB right now is 1, 1, 1 in the diagonal. The inverse is still 1, 1, 1. Okay? And what is my AN? AN is my -2, -1, 1, 1, 2, 0. Okay? So that's, I'm skipping some of the zeros. Okay. So that's how it looked like. And of course, because this part is 0, so what you will get in the end is -1 and -2. Okay, so what does that mean? When you go back to your objective function, basically your objective is like this. Your objective function is like this, but at this point, these portions basically tell you you are having -1, -2, and you are multiplying your xn. So what is my xn? Xn in this point basically is my x1 and x2. Why? Because we said the first two are the non-basic. So the corresponding variables basically are x1 and x2. And for the rest are x3, x4, and x5. Right? This is what we chose. So over here we realize the coefficient for x1 is -1. The coefficient for x2 is -2. Both of them are negative. So for LP, it's a good sign. That means, uh, remember the non-basic at the beginning, we consider them as 0. So it's like we at the beginning consider, it's like we consider non-basic variables as 0. So it's like if they are 0, you don't, uh, those negative coefficients doesn't help you to decrease the objective function because those are 0. So if we realize the coefficients of them are negative, then we can try to increase the value of either x1 or x2 so that my objective function will start to decrease, right? So this time we will want to choose one of them. No matter how many there are, we want to choose one of them. And we start to increase the value of it. So in this case, we will choose the most negative one. Okay, we will choose the most negative one. So in this case, -2 is the most negative one. So the corresponding variable x2 is chosen. And we wish to increase the value of x2. And when we increase the value of x2, it's no longer 0. That means originally it was non-basic. We basically want to convert it into basic. So this action is matching the way we categorize the variables. Originally it's non-basic. When we want to increase the value of it, we convert it into basic. So in this case, we convert it to basic variable. And whenever we do that, we need to choose one basic and convert it to non-basic. So it's like a swapping. We need to make a swap. So the very first step of LP is to find which non-basic change to basic by choosing the most negative coefficient in this vector. Okay? And when we complete the selection, the first half is finished. The second half of LP is to find another variable from basic and we convert it to non-basic. And then we finish the swap. Okay, is everything okay right now? Should be clear. Now we need to work on who to be converted to non-basic. In order to do that, we need to do some derivation again. And let me see which one do we use. We use so we are going to use this one. This was derived earlier. And let me move on to the next page. So over here, I'm going to introduce the second part. We choose one basic and convert it to non-basic. That's what we want, okay, to complete the swap. So how? Over here, we want to rearrange this in a certain way. Okay, and we are going to study the dimension of each term. So in order to do that, let's go back and get this figure. Take the whole thing, copy, paste. Okay, cool. Okay, so from here we can tell AB is m by m. AB is m by m. What is AN? AN is m by n minus m. And let's see, what is AB? XB. XB is n by 1. What is AN? AN should be n minus m by 1. AB inverse is the same n by m. B is n by 1. So by checking the dimension, you can tell the whole calculation is n by 1. Okay? Uh, so over here, we would like to look at these. These two. These two is m by, the together is m by n minus m. Okay? And how about these together? These two together is n by 1. Okay? And let's rename these two, the unique ones, rename them in a certain way so I could do further derivation. Let's rename them. Let's call this capital A hat, and let's call this B hat. So over here, A hat equals to AB inverse A, and B hat equals to AB inverse B. Okay, just to uh, uh, just to simplify the equation and make it nicer. Okay, so in this case, we could actually try to visualize in the following way. From this same problem, we know our xb, these are the basic, are x3, x4, and x5. So my xb basically are my x3, x4, and x5. Okay, so what is my A hat? My A hat basically is a matrix that has a dimension of m by n minus m. So n is the number of equations, so it's 3. Is it 3? Yes. And n is the number of variables, which is 5. So supposedly my A matrix is in the size of 3 by 2. So this is how it looked like. And what is my AN? AN basically is x1 and x2. And how about my B hat? B hat is n by 1, so I should have 3 numbers like over here. Okay? So we can rewrite the sum equation that we know in this way just to have a nice visualization of it. Okay, and in the first part, we already said this x2 was chosen to convert to be converted to be converted from non-basic to basic. Okay, this is what we already did in the first half. And since this is the case, we could focus on the relationship between all the relationship that is related to x2. Okay, so let me kind of actually reshape those. So let me reshape them like triangles, and these are like squares. Okay, just to allow you to know where those components are. And then now I would like to only consider the parts that has relationship with x2. So we are actually studying these. Why is that? Because x1 is 0. x1 is 0. S1 is the non-basic variable that is going to remain 0. So whatever that we have in the circle doesn't matter. It's going to be multiplying with 0. So we can get rid of it. So at the end, we have some equation on the right. What matters basically are those numbers in the triangular positions. Okay? And now we would like to do some. From here you can tell it's it's they are 3 different lines, 3 different linear functions, right? And you can actually make drawings of those linear functions. Before I make drawings of those, let me get the numbers of those. Okay, I have my A hat. So what is my A hat? I need this. Otherwise, I don't remember the numbers. Copy. Resize this. Move to here. And maybe use a marker to just this is what I studied earlier, and then I'm gonna paste my problem here. Let me do it again. I didn't copy the whole thing. Copy it, and then let me paste it here, but resize it and place here. And I'm gonna delete some of those, the ones I don't need. Okay, I don't need those. Okay, and I just need to remind myself those are the basic and those are the non-basic. Okay, so my A hat is AB inverse times AN. So what is my AB inverse? Should be 1, 1, 1 again. And what is my AN? AN should be my minus 2, 1, minus 1, 2, 1, and 0. So when we complete the multiplication, I basically have the exactly same thing, right? I have exactly same thing. But what matters actually are this portion, the one on the second column, because that's where my triangles are. That's Those are the ones that is going to multiply with x2. And whatever on the first column doesn't matter. Okay, so keep in mind I need those 1, 2, and 0. How about the other part, which is b hat? B hat is AB inverse times B. AB inverse is 1, 1, 1. What is my B? B is my 2, 7, 3. So at the end, I have 2, 7, and 3. Okay? So if I plug in, I basically have what? X3. I can actually now rewrite in this way. Basically, I have three functions, x3, x4, x5, plus 1, 2, and 0, x2, 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 equals to 2, 7, and 3. Basically, three different linear functions. Okay, and let's take a look at those linear functions and uh, have a nice observation. And now let's observe these in this way. This is the value of x2, and I'm gonna have 2 here, 3 here, and 7 here. Okay, what does that mean? Uh, 2 is my actually x3, 3 is actually my x5, and 7 is actually my x4. And the first one is should be like, the first line is like this. Second line is like what? Let me see. When I increase by, if when this is, so it's let me do this. Here should be 2, and here is 3.5. Should be this one. Is it? Yes. And the other one is like this. So the first line is actually this one. The other line is this one, and the third line is this one. If you try to plot out these three lines, it's actually like this. And why do we visualize this in this way? Because originally, originally x2 was 0 because it was basic. Oh no, it was non-basic. We want all the non-basic to be 0, right? And now we said we want to increase the value of x2. So as x2 increase, the value of x3, x5, and x4, they will be changing correspondingly. And the relationship between them basically are these three linear functions. Okay, and there's one rule. We cannot have negative values of x. So when x2 increase, one of it may become 0. So at this point, we realize x3 is the first one becomes 0, and you cannot increase x2 anymore. Otherwise, x3 become negative. So in this case, you actually increase x2 from 0 to 2, and meanwhile, x3 decreases from 2 to 0. So actually, x3 is the one convert from basic to non-basic because it becomes 0. And look at the other two, x4 and x5, they are still positive. They are not 0 yet. We don't even care what are the values. We just need to decide, okay, x3 should be converted from basic to non-basic. That's our goal of this process. But do we need to make a drawing like this all the time? It's too time consuming, right? So there is a easier way. We call them the ratio test. So how do we do the ratio test? We do it like this. The I B divided by the ij capital A. So I is number of variables, actually number of should be the basic variables. And J would be what? J would be, so M should be, I will change from 1 to number of basic variables, so M. So we will have B1, B hat 1, B hat 2, and B hat 3. So J will equals to 1 to N minus M. Okay, so we need to examine all those. Oh, sorry. J is not that. J is actually the index that represent the non-basic variable to be converted, no space, to basic. So over here, basically x2. x2 was to be converted from non-basic to basic. So over here, J should be representing x2. Okay? So let's look at this ratio test. So when we do this ratio test, we probably need to uh, get this. Oh, we need this. Copy it. And then let's paste here. Actually, no, don't do it yet. Let's move this to here because I have no space. And now paste for the ratio test. So in order to make this clear, I draw a separation. Okay, so now we do the ratio test. Maybe I just move this whole thing here. So these are the calculation that we had earlier, and we now work on the ratio test. So we are, what are the B? B are here. So we have 2, 7, and 3 divided by what? Aij. So J is representing the one that should be converted from non-basic to basic. So basically, the pink one, these are a capital Aij. So I basically divided by 1, 2, and 0. Okay? So when I do that, I get numbers of 2, 3.5, and infinity. Okay, so what are those? Those are actually the intercept on the x-axis. And this time we need to choose the smallest positive one. So what would be the smallest positive one? So it should be this one. X2 is the smallest positive one. And when we choose this one, we need to study, okay, which one is this ratio test representing? And from here, we know these are representing x3, x4, x5, right? Following the order. So in this case, we know x3 is chosen to what? Convert from basic to non-basic. Okay, so with all these, we have two decisions. First decision is that our x2 change from, take a look, what happened. We're almost there. So this is what we had earlier, and we need to make some changes. Okay, now, originally, we have non-basic, non-basic, basic, basic, basic. So originally, we have non-basic, non-basic, basic, basic, basic. Okay, so now we change. So these are representing x1, x2, x3, x4, and x5. We change the role. X2 and x3 swap their places. So now we have non-basic, basic, non-basic, basic, basic. So these are the new categorization. And so we repeat the process again and see what happened. Okay? Now we repeat. So this is a chance for you to see what's going on again because we're repeating the iteration process. I need to evaluate. We need to evaluate this. Copy it. So starting from now, we are actually in the second iteration. This is our second iteration. Okay, so let's try it. What is my Cn? N now, these are my N in the new decision. So my Cn become -1 and 0. And remember, they are representing x1 and x3. Okay, minus my CB. CB will be -2, 0, 0. Just follow the exact same order. But for here, we don't care about what they're representing. Just follow the order. How about AB inverse? AB, these are my AB, 0. Just follow the exact order. And I need MATLAB. MATLAB. So the problem of giving you a problem like this in the exam is that how do you do inverse? I can only give you a problem at most 3 by 3. Otherwise, you couldn't handle it. Let me see. Maybe I need to set up again for my MATLAB. How do I set up? Yes. Oh, I need to maybe screen capture from MATLAB. Okay, I have my MATLAB. It's should be broadcasting anyway. So MATLAB, let me do what is it? 100 210 and then 001 inverse. So I have. Oh, actually, I will ask MATLAB to calculate the whole thing because I have MATLAB. You don't have MATLAB in the exam, so poor you. But I'm sorry. Okay, so where's my pen? Here. So the answer I have is -5 and 2. So what do we choose right now? The most negative one. And there's only one negative one, which is this one. And what does it represent? X1. So this means X1 should be converted from non-basic to basic. Okay, so once you know how to do it, it's actually very quick. It's just that you need to do inverse. Okay, what would be the next? The ratio test. The ratio test is B I oh, so let's get the B hat and A hat. Okay, so what would be the B hat and A hat? It's right here. And I don't want you to memorize the equation. I will give you those, right? You don't even need to memorize anything. Okay, so let's get them. AB AB inverse is basically this guy. Okay, and we need it again here. Multiply. Here's B A273. AN is here. Here. Then you just need to calculate again. For me, MATLAB again. Where's my pen? Oh, here. Sorry. Okay, so MATLAB again for me. So this will be my A hat. -2, 3 and 1, 1, -2 and 0. Okay. Oh, sorry, my MATLAB was blocking the screen. Oops. This one. Oops. Yep. So, okay, I got it from MATLAB. And continuing this with my next calculation, I have 2, 3, and 3. Okay? And based on my ratio test, I need to do BI over AIJ. And what is my J? J right now is basically my first column because I know my X1 should be chosen. And BAIJ basically is this column, the first column, which is representing the uh, X1, right? So here for my ratio test, uh, I basically have 2, 3, 3 over -2, 3, and 1. And what does these three numbers represent? The three basic. And what are the three basic? X2, X4, and X5. So X2, X4, X5. And what are these numbers? -1, 1, and 3. And what do I do right now? Choose the smallest positive one. So this one. Okay, so X4 will be converted from basic to non-basic. Okay, so that's the end of my second iteration. We just need to do one more time. So one more time. So it's actually very fast if you have MATLAB, right? So now, oh, so this is the end of my. This is like uh, in the second iteration, right? And now we are moving on to my third iteration. And I know this time I swap x1 and x4. x1 and x4. So x1 and x4. They swap. So B and N for those. And for the rest, you don't do anything. Okay? And what do we do next? We do all these again. Okay. So what is my Cn? N right now are these two are N. Okay. Cn basically 0, 0. Where's my Cb? Is here. Where is my AB? AB will be like this. What is my AN? Don't forget the inverse. AN will be my 1, 1, 0, 0, 0. Okay, and what would be the number? Ask MATLAB. So negative, and MATLAB tells me negative 1.333 and 1.667. So it seems like we still have a negative value here. So we need to choose the most negative one. So which is this one. And what does it represent? It's representing this is x3 and this is x4. So did I make a mistake? Did I make mistakes? Hold on. Okay, this one is okay. Oh, my notes doesn't continue. uh, yeah, those are x. So this means x3. So x3 was non-basic. Okay, I think it's fine. I think it's fine. Let's continue and see what happened. Okay, so x3 will be converted from non-basic to basic. And we do ratio tests. And they're just here. Okay, MATLAB. MATLAB. So I have a bunch of numbers. These are okay. Okay, and what are these? These are 1, 4, and 2. Okay, and now I do the ratio test. So for the ratio test, you need to figure out which column from A should be chosen. And from here, you can tell because the first column was chosen to be converted. So I should study the first column for ratio test as well. Uh, so we have 1, 4, and 2 divided by these numbers. And what does these three numbers represent? The basic ones on the top. These are the basic ones. So x1, x2 follow the order. So we have this one. Actually, this is the smallest positive one. Actually, the only positive one. So we don't even need to calculate. We know xy should be converted from basic to non-basic. And we move on again. So when do we stop? I think we are stopping this time. So I will explain to you when do we stop. So in the fourth iteration, we realize x3 and x5 need to swap, 3 and 5 swap, so B, 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 and N. Okay, and let's figure out, if we do that, what would this value be? So N, these two are N. These three are B. Cn would be 0, 0. CB would be like this. And AB would be like, sorry. Let me just copy. Being lazy now. And inverse of it, AN would be like this. Okay, now MATLAB again. I think I made some mistake somewhere. I don't know where. So if you still having negative numbers here and there, you made some mistake. So you're supposed to stop when you have no more negative. So maybe one of my calculations screwed up. Usually is this one. Let me see. Maybe I had some typo here. So here is my, or sometimes you incorrectly make the swap. You swap to a wrong combination. 1 and 4. 1 and 4. So 1 and 4 stop, swap. Yes. So here it should be okay. MATLAB here is negative. I don't know why. I don't know what happened. Let's continue. Maybe it just takes time. Okay. Oops, sorry. So what are those representing? X4 and X5. So this is X4. It seems like you need to convert n to basic. Okay. And do this again. And here I should have those. Oops. Okay. The value should be looks all right. I don't know. Later on, we will make a drawing of all the functions and we can visualize what happened. Okay. Okay. So this time, supposedly, we are studying the first column because here the first column was chosen. And let's do the ratio test. And from here, you can tell this is the only positive one, right? So, so let's swap 2 and 4. Let's see what happened. I hope this is the final version, final iteration. I want to go home already. So 2 and 4. Do the swapping. 2 and 4. Fifth iteration. So B N B B N. So these two are N. Now, so Cn will be -2 and 0 minus Cb will be these. AB will be the inverse of this. AN would be these. And let's see what MATLAB tell us. No! I don't know why. What happened? Okay, now I feel strange. Let me check here. Let me check here. Because sometimes your ratio test is wrong. Uh, this is right. This is right. Shows the first column. Okay, now I can teach you a trick. I feel strange. So I would like to make a drawing of this problem and see what happened. Then I probably will realize where I made a mistake. So, uh, here. Oh, I don't need the negative part. If I do this, so this will be my x1 smaller than 3. So here's my x1, here's my x2, right? So I have my third equation ready. How about the other one? Uh, I would like to make drawings like this. X2 smaller than 2x1 plus 2. The other one, x2 smaller than x1 over 2 plus 3.5. So I should have a 2 here and 3.5 here. And the slope is 1/2. 1/2. So I should have a point or 2. Oh, this is by 2. So I should pass through this point. Uh, okay, precise enough. And the other one, I should have something like this. So this will be my, here is my oops, G3, and they are both smaller than, so the top is gone. And here is my G2, the other one is G1. So we are actually studying inside this domain. Okay, so we try to find a solution over here. And what does the object function look like? Let me use a different color. So when I have a position of 1 and 0, 1 and 0, my f equals to -1. So when will I have the same value? I think it's here. So when I have 0 and 0.5, my f is also -1. So my contour actually look like this. So when I move along this direction, my f decreases, right? So by visualization, this should be my optimal, because that's the position where my f should be the minimum within this boundary. Okay, and supposedly you need to do this LP for 3 times. So I think I made a mistake somewhere. I don't know where. Why 3 times? So initially, when we say the first two are non-basic, that means the first two are 0. So actually, at the beginning, we start from x2, x1 and x2 equals to 0. So in the figure, we actually start from this point. Not clear enough. Maybe change change a color here. Okay. We actually start from here. That's our 0, 0. That's our initial point. And when we move on to the next position, we realize uh, what are x1 and x2. So over here, we realize x2 become non-zero. Okay, but what is the value of x2? It's actually here, this point. Because when we try to increase x2, some other value decreases until we couldn't increase x2 anymore, and actually that will force us to stop at that point. Okay, so that's where we said that's where x here x3 x2 become 2 and x3 becomes 0. Here x2 becomes 2, x3 becomes 0. Okay, so we actually move on to a position where x2 is 2. So it's right here, 0 and 2. x2 become 2, right? And now we realize in the next stage, we are focused on x1 and x2. They both, x1 and x2 become non-zero. Okay? So supposedly, we are moving on to this point, actually. We are actually moving along these directions. But I think I made some mistake right here. Why? So it's this page. Is it? I think I already made mistake here. Uh, I said x1 and x4 swap. 1 and 4 swap. 1 and 4 swap. Here we still have, so if in the fifth, if in this iteration we have both positive, then we are happy. So maybe I made some mistake here. Uh, non-basic is like this. This is basic. Maybe my MATLAB was wrong. Uh, okay, is right. Unfortunately, my MATLAB was not wrong. So maybe some of the decision was wrong. Uh, but the idea is to continue until your check right here become all positive. Then you can stop. But if you made a mistake like this during the process, you will be moving along the edges because this is a 2D problem, and we expand the dimension of this problem into a 5D problem. So we cannot visualize it. We can always check how x1 and x2 are changing, but we cannot visualize 3, 4, 5. And from the behavior right here, you realize linear programming is trying to move from intersection points to intersection points. And supposedly you should be moving from here, here to here. So you should be doing that calculation 4 times. Once here, and choose one side, either go this way or go that way. So when we have two variables to choose, either go here or go there, we could decrease the objective function. But we said we should go toward the direction where we can decrease f fastest. So we said we should choose the minimum, the most negative one. So that's where we believe we could decrease f the fastest. That's if we go this way, that coefficient is smaller. Is more negative than going this way. But we don't know if we go this way. The next time we can converge. We never know how many intersections are there in the future. We can only move from edge to edge. So when we move to here, we only have one option. In our calculation, you realize when we move on to the second stage, right here, we only found one negative value. That means only one variable can be chosen, and that means you can only move along one direction. So actually, linear programming is trying to follow that boundary, edge by edge, and moving from one intersection point to the other intersection point. Until you move on to here, supposedly your uh, checking equation should give you both positive. That means you could not decrease the uh, objective function anymore. You should stop. But I don't know what mistake I made in during the process. So unfortunately, I couldn't show you the right process over here. Maybe I could give you a homework and then you could do this and let me know. Let me know where I made a mistake. Okay, so that's pretty much I want to introduce today. I will send you photocopies of this, and also I just live streaming the lecture. I hope the video condition is good. So if you miss anything, you could go back and check. And if you found a mistake during the process, you can, comment in the video. Okay. So I can make a cut.